Hey, hello everybody. So this is your TA for the Mechanics of Materials 2 Summer 2020 Design, Mechanical Engineering Design 2 course. This video is one of your required asynchronous lectures that you have to watch for your review for Mechanics of Materials. And hopefully the stuff we cover in this video helps you with the projects or assignments that we task you throughout this term. So let's just go ahead and get started. In this recording or lecture, I'm going to be covering the topics that are referenced in these two literature, Advanced Mechanics of Materials and Applied Elasticity by Ergel, and the Advanced Mechanics of Materials 6th edition book by Boresi. This might be different from what you guys used for your Mechanics of Materials textbook in the introductory class. What I hope to cover today is sort of a review of what you guys have gone over from prior courses and hopefully adapt and explicate further topics so that you have a better understanding of how to apply them when you work on your problems. So the first topic we're going to talk about is Mohr's circle. Now I'm starting with Mohr's circle because it is a fundamental understanding in mechanics of materials it's a fundamental technique in mechanics of materials to sort of understand the state of a system by simplifying it into this method. So Mohr's circle essentially is a useful tool to analyze the entire state of a system when it undergoes load. So let me just go ahead and start writing things down. So Mohr's circle, simply a method of observing the stress and strain state of a material at different orientations. Okay, so that's pretty much obvious. We have the advantage of observing the entire state of a material in a 360 scale. For a 2D element, and we'll start off with 2D Mohr circle first. We'll develop into 3D. We can observe its states at any angle using transformation equations. So the beginning of Mohr's circle, the foundation of Mohr's circle starts off with transformations of stresses into different orientations. If we're interested in the stress state at multiple different angles. So let's start off with a simple element that is undergoing stress states in all faces, normal stresses. So we'll call this sigma x, we'll call this sigma y, and it also undergoes shear stress, positive shear stress, tau x, y. And so if we're interested at rotating the element and seeing how the stress state behaves that way, for example, if I decide to take this element and rotate it as such, what is this resultant sigma x prime or sigma y prime, and then tau xy prime, etc., etc. The general equations are simply our transformation equations, and they are as follows. Sigma x prime is generally, or typically, sigma x plus sigma y. By the way, I'm forced to go through these slowly, given my technological limitations. So if you guys want to go ahead and skip through this part of the video until I'm done with the equation, feel free to do so. There might be times, I haven't decided yet, where I'm going to edit the video and skip some of the writing out of these equations or derivations myself. So tau xy sine 2 theta. Okay, so that's the first transformation. Next transformation, sigma x plus sigma y over 2, this time minus sigma x minus sigma y over 2 times cosine 2 theta minus tau xy sine 2 theta. Okay. And finally, the transformation for the shear stress will be given as negative sigma x minus sigma y over 2. So implied in parentheses sine 2 theta. Theta, by the way, being the orientation angle that you change from the original coordinate system to the new prime coordinate system that you want to evaluate at, plus tau xy cosine 2 theta. Okay, so now that we have this transformation, generally what's understood is that when we transform this, we essentially go in a circle, which is why now we start the formulation of Mohr's circle. In essence, what happens is we are evaluating stress states in a circular angular form. So it's best to put this in a visual interpretation that we can fully take advantage of, so we can establish a system of equations and understand how the whole state of the matter of a material behaves just from looking at a simple plot or a simple useful diagrammic tool. So let me go ahead and draw out the circle. So here's what a generalized Mohr circle looks like, having shear stress in the y-axis or vertical axis and normal stress in the horizontal axis. Mohr circle essentially is developed by choosing 2 points, the first point being whatever given stress state is for sigma x and tau xy, followed by whatever your given stress state is for your transverse stresses or stresses in the y direction. Now there's always this coupling with tau xy. So it really doesn't matter if you put the negative here or you use the negative here. It's wholly dependent up to you. If you don't really understand this development, all you need to know is that there's always going to be 2 points, one with sigma x and tau xy or negative tau xy, and the other one with sigma y and the opposite sign. So using this equation, we can essentially go from one state and go around at an angle to another, which is basically the whole advantage of Mohr's circle. Now we can essentially create an equation that represents the entire stress state. So essentially we can just draw a diameter line in between the 2 points here. So didn't really draw that well. Let me try this again. So essentially the center of the circle is somewhere around here, right? And obviously we have a radius r for the circle here. And if we want to go from our normal stress state from if we want to go from a completely normal stress state onto our current stress state right now, we simply need to transform it by this angle. I'm going to call it phi here. Okay, so the development of the equations for Mohr's circle. So we have an average stress here, which is going to denote as stress average, a stress average, and a radius. So if you guys remember the equation of a circle, it's something like a squared plus b squared equals the radius squared. We basically take that same notion to develop the equations for Mohr's circle, where we try to essentially state the stress states at this point right here and this point right here. which we would denote as sigma 1 and sigma 2. Okay, so that development, the equations are as follows. Sigma 1 or 2 becomes first sigma x plus sigma y divided by 2 plus if you want sigma 1 minus if you want sigma 2 plus or minus the square root of tau x y squared plus sigma x minus sigma y over 2 squared. So if you understand the basis of this equation, this section right here is essentially your average stress. This section right here is representative of your radius. So there we go. We essentially have a system, a set of equations we can use to develop a whole idea of understanding the stress state of a material with given applied loads. Now, this phi right here, one of the biggest advantages of Mohr's circle, again, is you can look at every angle. This phi right here, from stress state, or we're just going to say principal stress state 1 to principal stress state 2 here. This phi right here is double what the actual orientation axis is. So if I could draw it right here, for example, right? That's the x and y direction, and we have a principal direction 1 and principal 2 direction here. Rotating it from the x to y system would just require rotation theta, but here it will require 180 degrees, where here it would be a 90 degrees. So generally, we put phi as 2 times the orientation, the real problem statement. So that's why there's a 2 theta here, just to encompass the fact that we have to double the rotation angle to encompass the real state that we're looking at. So now we have to understand this. Let's go over principal stresses for a second. So I mentioned principal stresses. Okay, so I mentioned principal stresses as the radial components of the Mohr circle that don't have shear stress. And essentially, the whole idea is we can boil down the entire stress matrix into essentially 2 equivalent stresses. For a 2D case, it will be 2 equivalent stresses. For a 3D case, it will be 3. And the advantage of this is, one, we identify what the equivalent maximum normal stress is at what angle an identifiable system is, and 2, we have the luxury of not dealing with shear stresses, which is advantageous for quicker and more robust calculations. So there's a lot of interest in trying to achieve the principal stresses. So that is for a 2D case. So for a 3D case, the formulation is a little bit more difficult. We can't rely on the simple use of transformations to create our visual Mohr circle. So what we're going to have to do is we're going to have to use some basic mathematical principles to achieve our 3D stress state. So it starts off like this, and it utilizes what we know as the principle of stress vectors. So you basically have the stress state here. Okay, let's see. Everything's really symmetric here until sigma z. So if you multiply the stress state of a 3D system with particular principal stress directions, particular directions, we'll say, you'll achieve the equivalent system when you multiply the principal stresses, or theoretical principal stresses. Any off-diagonal term here is just assumed 0. So multiply those stress directions by the same principal stresses, or principal stress directions, and you achieve basically a singularity here. So we can take advantage of this mathematical assumption and move this to the other side. So I'm going to simplify this. This I'm going to call bracketed sigma x, y, and this right here I'm just going to call bracketed regular sigma. Okay? So essentially we have as the following. I'm getting hold on, I'm a little sloppy here with my notation. Subtracted by some arbitrary principal stress direction, and I'm going to basically term the principal stress directions as a n vector here, vector unit vector n. Now the whole mathematical philosophy or principle behind this is use of Lagrange multipliers. I'm not going to get into too much detail of that. Just know that this is inspired by a already established mathematical principle to achieve our method of finding what the maximum normal stress is. Now, if you think about this physically, right, the unit vectors cannot equal 0, obviously. It has to have a directional substance, so this cannot be 0. Essentially, everything within this parentheses has to be 0. So not without going into too much the mathematical terminologies, we could just think about this physically. Here, this is essentially a singularity here. So whatever arbitrary principal stress you have, multiplied the identity matrix to get this diagonal column matrix there. This and this are essentially describing the same state, just in two different models, essentially. So if this were true in the mathematical term, we call this a singularity, and we would say that the determinant of whatever's in the parentheses, so for completeness sake, the determinant of the stress state minus the an arbitrary principal stress times the identity matrix must equal 0. So this must be true, since they again describe the same state or same state of a material. So if you go about this analysis and determine how to find the principal stress, you basically, and let me just go ahead and write it right here. You get the following polynomial equation, where is your arbitrary principal stress times what we call the first invariant squared plus second invariant times arbitrary principal stress minus the last invariant here. And these invariants are just achieved by going through and doing the calculations for the determinant. I'm just going to go ahead and write out what those invariants are. The first invariant is equivalent to the trace, what we call the trace of the stress matrix, which is simply the sum of the diagonal terms. So it's sigma x plus sigma y plus sigma z. Okay. The second invariant is given as sigma x, sigma y times sigma z. So each diagonal term multiply with one another, plus the off-diagonal terms squared. Sorry, not plus. Subtracted by the off-diagonal terms squared. Is x, oops, y, z squared. I'll fix that in post later. And finally, the third invariant is simply doing the determinant of the stress matrix itself. So if I write that out in completion, that would be sigma x, sigma y, sigma z plus 2 times tau xy, the off-diagonal terms again, tau yz, tau zx, plus sigma x times tau yz squared plus sigma y times tau zx squared plus sigma z tau xy squared. Okay, so essentially you will achieve three constants that you can input into this polynomial equation here, and you guys remember how to solve the roots of a polynomial equation. You essentially get your principal stresses as the roots of this equation. So just for notation's sake, we always say that sigma 1 is greater than sigma 2, which is greater than sigma 3, always in that order. And so if I were to draw out Mohr's circle again, here being the shear axis and normal stress axis, what I would do is I would identify where sigma 1 is, sigma 2, and sigma 3 here. Okay? So with that, we have a Mohr circle that not only identifies a stress state between two principal axes, but and also the principal axis from 1 to 3 is this entire large circle over here. But the biggest advantage also is that we can find where the maximum shear is, which occurs right here. And generally, which is correspondent to the center, generally the maximum shear, so it will be tau max. The maximum shear would be equivalent to, so tau max would be equivalent to your largest principal stress, which we identify as sigma 1, minus smallest principal stress for 2. So essentially that's the radius of this circle here. And yeah, that essentially establishes the entire stress system. The maximum normal stress is obviously being in the only in the principal stress directions, and the maximum shear stress occurring here. And notice this right angle right here is phi of 90 degrees. Phi of 90 degrees is the equivalent of 45 degrees. So in a physical system. And we'll go over this when we go over failures, but typically this has some significance because if you see how a material typically, let's say an isotropic metal, for example, fail, when you put it at a uniaxial tensile test, you typically see a fracture that's almost 45 degrees to the face that you're applying normal stress in. So that's obviously that's an important state to understand. And you can carry this idea into strain Mohr circle. So strain has its own Mohr circle where you have, I'm going to draw this very crudely here, shear strain here, normal strain here. Same theory applies. You have your principal strains here. This is epsilon 2. Sorry, I kind of wrote this a little sloppily. Okay, so yeah, you can essentially find your principal strains here. And also you can find your principal stress directions too. So back to this equation here, once you find your principal stresses, you essentially apply one principal stress per iteration to find where your your principal stress directions are. With the additional equation that you need to know, which is, let's see if I write it here, that for whichever principal stress direction you're analyzing, the eigenvector, the unit vectors must all add up to 1. Okay, so that's essentially how you find your principal stress directions. You can do the same thing with your principal strain directions. I think the biggest thing to note here is that your principal stress directions, let's see, insert text box. Okay, your principal stress directions and your principal strain directions these do not coincide with one another. So if you imagine us holding a cube, for example, apply a normal stress here. And let's say I apply only a transverse stress here, and I don't apply shear stress, you could probably imagine the cube forming something close to this. Well, this is pretty much exaggerated. This kind of looks like a pure shear deformation. But essentially, one of our major principal stress directions, principal strain directions is that way, and it doesn't correspond to our, well, I meant to say this was our principal stress direction. Principal stress direction 1 and 2. So they don't necessarily correspond to one another. I should, for completeness sake, since I kind of made this a pure shear diagram, I might as well put whatever. So you can see that in this case, they don't really correspond to each other, and that's typically true. You also have derivations of continuum mechanics that can prove that they also don't align as well. I'm not going to go through that. Just know that these directions are not parallel to one another. So that's essentially it for Mohr's circle. Now we're going to go on to the next topic,